Okay. So explain what happens to the slope values as you move from left to right with a fixed y value. So if we are looking at this guy, we're moving from left to right. Now we're at a fixed y value. All right, it's y value. So if we are at a fixed y value, I'm just going to pick this guy, let's say right here. Okay. All right. Now as we move across, if you notice that if the derivative, if y prime is actually greater than 0, then he's actually going to decrease as he goes across. But if we pick one down here, if he's negative, then he's going to increase as he goes across. Okay, so that's how we would just say things. Like if they're asking you to interpret, okay, explain what happens as a slope value if y prime is, what was it at the top? It was if it's greater than 0, okay, then y prime decreases as you go from left to right. Okay, and I would just include if as you go from left to right. Okay, semicolon if less than 0, if it's negative, okay, like right here, as we move from left to right, he actually increased. Okay, as you go from left to right. Okay, now explain what happens to the slope values as you move up from x-axis with a fixed x value. So, as you move up, okay, starting low, if he is negative, he'll become positive, and if he is positive, he will become negative. But let's see here. Well, that's the end game, but remember, he does actually go vertical, so maybe what we should say is that, what is this guy? Let's pick one that's actually closer to the center here. This guy is, he basically, if he's negative, okay, and then he's going to decrease, go vertical, and then actually go positive, and then decrease. Okay, so we don't have to write that, but like that's just the idea. Imagine staying at a fixed x point and just travel all the way up. Okay, we don't have a lot of detail here, and you know, when we drew this, like I should have marks on every single one that would make this a little better. That's why these are good right here, because the density of the tick marks or the slopes, tangent lines, whatever you want to call them, are kind of more vivid. Okay, you can see the pattern a little better. Okay, so for time, I'm just going to keep moving here. Now, what if? Now, this is probably what's going to happen on the AP exam. Almost guaranteed. If you see a question on slope fields, it's going to be probably matching. And so what you do is, you actually don't have to necessarily, you don't have to sketch anything. You can just kind of use the logic of what's actually happening with these slopes as you either go up or down, left or right, and you're just picking up particular patterns. Okay, now on the back here, what we're going to do is we're going to have kind of have 5 rules of thumb. That will be very helpful. But what I want to do is I just kind of want to show you the logic that is going to be embedded in those patterns. Okay, so I'm just gonna kind of glance through here and find some things that I think stick out. Okay, so first of all, probably what sticks out the most for me are the ones that are missing these batches. Okay, so if you're missing an entire kind of domain, right, or a range, then you know that there's restrictions. There's some things that don't exist for the particular equation. And so what I'm going to do is I'm going to go through here and I'm going to look for the ones that actually are going to have DNEs, right, that just will not exist. Now I'm looking for, I can't have logs of negative numbers. I can't take the square root of negative numbers. And that's kind of it, right? Those guys are kind of the ones that stick out, okay? So if we looked here, let's say that we'll just start with number 1. We've got the square root, okay, so square root, and it looks like I can have x equal -2. I can have a square root of 0, but I can't have a square root if x is smaller than -2. If it was -3, I would be taking the square root of a negative number. That can't happen. And so what you're seeing here is you're seeing that x, if it's just x here, it looks like that I actually can't go past this direction, okay? I cannot, this is like where -2 is, probably, and I don't even know what the tick marks are, where they are, but it doesn't matter for slope fields. And so it looks like there's definitely a domain restriction where you're not going to, there's a whole basically empty space because you cannot actually go to the left of -2, okay? All right, so that's D. Now, I didn't even look at the other stuff. You don't need to. When you're doing slope matching with this kind of density, you're just looking for, okay, how is the general flow of things, okay? You don't have to nitpick and find out at every location. You're just looking for patterns. And what I also want to point out too is that this only has an X, okay? So let's actually write this. Yeah, it's part of kind of what that's kind of an important part here. And what I want to do is I want to see that there's no Y for me to actually change, okay? There's no Y for me to change. So what you'll notice is that if I have a value for X here, okay? If I have a value for X, here's the slope is almost 0. Then it looks like I'm pretty close to -2 there. It looks like, notice that all my Y's were the same. My one particular value gave me the same Y because there's no Y is not changing as I'm going up or down, okay? That's going to be true if there's a Y and there's no X, okay? If the Y is, if you can plug in a number into Y and there's no X to plug in another value, your Y's are going to be consistent as they move across, okay? And so what I'm going to do is I'm also, in my next stage, after I take care of this guy, I'm going to look for the ones that are only X's and the ones that are only Y's, okay? And those are going to be easy to kind of knock out, okay? Now the ones with X's and Y's, those are the ones I'm going to have to pay a little bit more attention to because as one is changing, the other is changing. For example, this guy, it had X's and Y's, okay? X's and Y's, right? Equation, yeah, X's and Y. It had an X and a Y, all right? Okay, so the next one is this guy. It looks like there is an absolute, I can have no negative numbers, all right? And notice too that the Y's are consistent going across, which means there is no X value, okay? And the only thing that actually has, I see this guy right here, there is a natural log, there's a log, okay? And it looks like there's no X's. The X is not changing as we go from left to right. It's staying consistent. That has to be it. Okay, that has to be it. Now notice that I'm playing kind of a logical game here, right? I'm not actually interested in the actual location of a particular solution. I'm just looking at the field and patterns within it. All right. So these guys are going to be two of the easier ones. Okay. Now I want to look at the ones that just have X's, okay? And I'm going to put a check mark for the ones that just have X's. Okay, so these guys just have X's. It looks like I'm going to put an X on the, I don't know why, let's pick something else, a circle on the ones that just have a Y. Okay, and it looks like that's the only one. This is the only one that just has a Y. Let's look at the ones that just have the X's. So what we're looking for now is if there's no Y, okay, that means that we're going to stay consistent as we go up and down. The only thing that's changing is when we go left to right, okay? So with cosine, okay, what I'm looking for is I'm looking for a change where, well, here, we can do another trick. Think of it like this. The derivative, I'm sorry, the antiderivative would be y equals sine, right? Okay, so what I'm looking for is the sine pattern within it. Now, you can do this sometimes. You can actually just take the antiderivative and think, okay, what looks like sine, okay? Okay, now this kind has got a wave function here, but it looks like it's kind of like a negative sign, and then it kind of flattens out. So that's not it. That's definitely not a trig function there. This is kind of it, but then you'll notice that these strips here, these diagonal strips, have like a slope of -1 as you go across. It doesn't look like I can draw like a sine wave here. That's definitely not a sine wave. This looks like it's got something else, a sine wave going this direction. But this guy right here, this looks like a sine wave as I go across. That's it right there. And then these all represent the families that you could have with that plus C. Okay. All right, so it looks like that guy is H. Okay, now you'll get faster at these. I'm just kind of explaining my logic. They won't be taking this long. All right. Now this guy, this is another one where only the x's are changing as we move from left to right, but not up and down. Okay, and if you look carefully, there's only one of those that does that. Okay, if you look at A right here, notice that as you go up and down, it has a consistent pattern here. That means that there's no way, you can't put in a y value for it to distort as you move up or down, okay? So he's consistently the same slope as he goes up and down, and you have to choose him because all the other ones have x's and y's. They're changing at the same time, okay? So this guy, you don't even know what he looks like, possibly, right? All you got to do is think of the consistency of the pattern and also what you have to choose from, okay? All right, what else? Okay, we got a trig function here. Oh, you know what? This guy right here, this guy's only y. So we're looking for something that's only changing. It's consistent going across, okay? Consistent going across. You can also look at it like this. If I'm going to take the antiderivative, I know that y would have to be, well, what would this be? This would be 1/3, or the antiderivative, I should have said. Y to the third, right? So can you see a pattern there? Yep, okay, this guy. Notice as we move across, you see the consistent y pattern, okay? And at each value of y, it's consistent. It's the same because there's no x that's changing along with it, okay? So the answer to this guy is C, all right? All right, now when you guys get back tomorrow, I've got a matching activity for slopes for you guys to work on, so we're gonna, again, practice this one more day, all right? So it takes a little bit getting used to. I didn't think these were particularly easy when I was a kid. All right, I got 3 left, right? 1, 2, 3. So this one right here, okay. Now, the way, let's see, when I was working with this yesterday, I was trying to think of like, what are some patterns here? This guy has an x and a y, this guy has an x and a y, this guy has an x and a y. So these guys, what do I have left? Let me cross out the ones that H, okay. So I got 3 left, okay, 3 left here. All right, and they're all weird, okay, they're all very weird. But what I want to do is, I think I'm gonna focus on this guy, and I'll save the trig last. Okay, I'll save these 2 trig functions last. But this guy is just negative x times y. Okay, so this means that I could kind of break out a table here, right? Do you guys notice that if x is 0, okay, then the derivative is 0, right? And when y is 0, the derivative is also 0, okay? So let's look at the ones that we have left and see that when x is 0, the slope is 0, okay? And when y is 0, the slope is 0. Okay, let's look here. When x is 0, the slopes are not 0, okay? They are not 0. These guys are changing, okay? Also, the y is changing. It can't be this guy. This guy right here, as we move across, nope, they're changing. These are not slopes at 0 when x is 0. Okay, this guy, there we go. look, we got when x is 0, the entire derivative has to be 0. Here we go, we're at 0. Now this guy, we can't see it because it's actually, the flat line is on the y-axis, okay? So these are all 0, and this is all 0. Do you notice that I don't have to worry about any of the other things, okay? I can just focus on characteristics of these guys so I can use the matching, okay? In the real world, people use technology to develop these slope fields. You saw the grapher, okay? When you're doing this on the AP exam, you are literally just going to kind of pick them out of groups, okay? It'll be matching. They don't grade slope fields. Like, you're not going to sketch a slope field for on your exam. All right, now we got these guys left right here, okay? Now, there's only really one thing that you can do with these two, all right? And if you look carefully right here, if you're going to take the cosine of something, okay, these guys are changing. If you're going to take the cosine, you are basically trapped, okay? When you take the cosine of something, you are absolutely restricted. Okay, this guy cannot be, you cannot have a slope that's larger than 1, and you cannot have it smaller than -1. This guy, because he's a trig, is squeezed in between having -1 and 1. That's it, okay? There's domain restrictions is basically all I can say. Okay, now if I look at, let's just start with G. I only got 2 left. I got F and G. All right, now notice this is a weird function. Like, we don't even graph that kind of stuff. This is really strange, okay? We never graph that in pre-calc because it's very rare. But if you notice here, at this guy, you'll notice that I have slopes that are definitely more than +1 here, right? Just looking around, those are greater than 1. A 1 slope should be a complete diagonal, okay? I can't have anything go over that, and I can't have anything go under that, okay? These guys don't do it, okay? This one right here, let's just test that and make sure, okay? You guys see the diagonals there? Okay, that's as steep as any of these go. They don't go any steeper. You don't see any of that. You don't see any of that. Okay, they all fall between these parameters here. So it has to be F by that property, and then this guy has to be this guy because he's the only one left. But what you can say here is, if you're taking the sine of y, I don't know if you can see it, but there's kind of a sine function going along here sideways. I wouldn't use that as a rule of thumb, but you can kind of see that that's what's going, the sine is traveling along the y-axis instead of the x. So that's pretty much the only way I would think of using the process of elimination for that, okay? All right, now this was an important piece, okay? All right, so we're kind of running out of time here. This is a long one. This one right here, we've got a differential equation at a point, 0, 1, and we got this guy. It's already graphed for us, okay? We're going to use a slope field to sketch a particular solution through that point, and then use integration to find the particular solution of the differential equation, okay? Particular solution through the point, then use integration. Okay, so we've got 0, 1. 0, 1. Okay, so what we're basically practicing here is that this guy is this is a field, okay? So what would his antiderivative be? Okay, if you can try to think here, if you remember, the antiderivative of this guy would be a log. Okay, now what do logs basically look like? Okay, they look like this. Okay. Any kind or something like that. Okay, they're inverses of exponential functions. Now, I don't know if you guys can kind of tell here, but if we know that this, you can see that this guy kind of like flattens out as he goes across, right? Okay, and then as we come around here, it gets real steep. And do you guys notice that they're basically, it has to get steeper and steeper. Like, there's got to be an asymptote right here. Okay, there has to be an asymptote. Because we can't actually equal -2 here, okay, it would be 1 over 0. So we would actually have a vertical asymptote right here. And so what this guy probably looks like is something like this, okay, as we go across, okay. It takes practice to kind of make sense of that. There could be some variation. So just a second. Yeah, quick question. Sure, yeah. All right, okay, so that's our graph. That's all you have to do. And now what we're going to do is we're going to do the antiderivative for this guy, and we're going to pass it through that point. And I think we've already done stuff like that. So let's go ahead and do that. All right, now this follows the 1 over pattern. You could just do a U if you wanted to. You could also do this. Let's say that okay, take the antiderivative of both sides. All right, and so now you are just left y. All right, this is how it plays out algebraically. The antiderivative of this guy, if you can imagine u would be x plus 2, but you really don't have to do substitution. There's no weirdness going on. This is a straight cut and dry thing here, okay? And then we would have plus c, but it's got to pass through a point, so let's plug it in. If we, let's see, if we plug in a 0, okay, so this is our general solution. Now we're going to get the particular solution. So let's plug in a 1 for y, 0 plus 2 plus c. All right, so 1 equals the ln of plus c. So if I want to solve for c, c equals 1 minus the ln of 2, because the absolute value of 2 is 2. All right, so this means final answer is y equals the equation of this curve. Equation of this curve is the ln of x plus 2, absolute value, plus 1 minus the ln of 2, because that is your plus c. Okay? All right, so what are the couple rules here? I know, whoa, long. All right, so well, this will basically add up to an hour, I think. So let's make a rule of thumb here. So dy dx, okay, as if it only has an x, okay, we said that if it only has an x, that means that as you move across, okay, it changes changes left to right only, okay? And then also dy dx, if it only has a y, then it only changes up and down. Okay? All right, now if you've got both, okay? If it has both x and y, okay, then what is happening is that both are going to change kind of simultaneously, and you're going to get a lot of funky changes, okay? Okay, now those are the ones you kind of want to watch out for, okay? These are the kind of the easy ones to spot, okay? What else? You also want to find out, find conditions, special conditions, okay? Find special conditions which will make the derivative of x positive and where it will make it negative. You're just looking out for those things. You don't have to know exactly what they equal. That's the whole point of the matching, okay? And then finally, last thing is look where dy dx equals 0 or undefined, okay? You're just looking for those key ingredients, all right? And that's it. Oh, homework. Would you guys, work on it as fast as you can? I know it's supposed to be like your skip day and everything, but you can chip away at it. We are at that crunch time. When we're done with the test, we can relax, okay? We have It's fixed time. Have a good day. Enjoy yourselves and do your homework.